Hello everyone, so we will be looking into one of the most interesting concepts in Olympiad mathematics, the chicken-foot lemma. So it's a relationship between in-center and x-center, and the theorem established from that is what we call as the chicken-foot lemma. So we have the triangle constructed here, ABC. So let's draw an angle bisector for vertex B here. Let's do the same for the other 2 points. And we can see that there's an intersection between these 3 angle bisectors, and we call this as the incenter. Now we can draw a circle around this triangle. So a circle touches the vertex of the triangle, exact point. So we can see this triangle, and we can extend the angle bisector of angle, let's call this angle A, and we can see that it intersects with the circumference of the circumcenter. And we can see that this divides the angle in equal halves, so it will also divide the arc in equal half. So we can see that L is the midpoint of the arc BC. Now what we are going to do is, what we can do here is, if we construct a triangle LBI, so let's draw this triangle here. We draw this triangle over here, LBI, then we can see that if you were to look into angle LBI, this total angle, so it would be the sum of angle LBC and angle CBI, right? So angle LBC and the sum of angle and angle CBI. So we can use the relationship over here of the inscribed angle theorem over here. So we can see that this angle LBC, right? Here the same arc for angle LAC as well. So according to inscribed angle theorem, so let's look into inscribed angle theorem first. So according to inscribed angle theorem, if you have a circle here, let's say this is point A, point B, and point C, and they share a chord. Okay, and we draw a chord here between this point A, and let's say that this angle created is alpha. Now we create another endpoint D and write the chord along the same arc BC. Then the angle here, angle of the point D, will also be the same. So as long as they share the same arc, they will have the same angle. So that's what the inscribed angle theorem says. So if you look into this, we can see angle LBC has this arc LC, and LAC also has this angle, also has this arc LC. So we can say that angle LBC is equal to angle LAC. Now, why are we changing LBC into LAC? Is because we know the value of LAC. LAC is half the angle of angle A. So we can say plus CBI. So we can say it is the half of angle A, whereas angle CBI is the half of angle B over here. So half of angle B. So we have angle LBI as this. So now we can also look into BIL, angle BIL as well. So if we analyze angle BIL, we can see that angle BIL is this angle over here, is the external angle of triangle ABI. So according to external angle theorem, if you draw this triangle over here, B, A, and I, and this angle, we can consider it as the external angle. Now the external angle is the sum of the two angles that is far away from this angle, not the closest one to it. So if this is x and if this is y, then let's say this angle would be like alpha, so alpha would be the sum of angle x and angle y in this case. So similarly, what we can say is the angle here BIL is the sum of angle B of angle ABI and angle BAI BAI. So the angle ABI we know is half of angle B, and BAI we know is half of angle A. So we know that now angle BIL. So we can see that angle BIL and angle LBI is the same. So angle LBI is equal to angle BIL. Now in an isosceles triangle, when two angles are the same, we can also say that their sides are also equal. So similarly, in this case, we can see that this angle and this angle, they are congruent. So we can say this side and this side, they are also equal. So if we follow this proof for other triangles as well, like for triangle L, I, and C, then we will also be able to establish the relationship that the angle, then the point L is like uh, the point L, if we extend it to point C, to point I, to point B, then it will have the same distance. So what we are going to do is, so we have established the relationship that LB is equals to LI in this case, right? So let's pause. So we have established the relationship that LB is equals to LI. Now what we can do is, this side AB, we can extend it, and we can do the same for this side AC. And then for this external angle, if we bisect it, and do the same here, if we bisect it, then here comes an intersection. And if we extend this angle bisector of angle A, then we can see that there's an intersection, which is the excenter. So we can call it IA. So IA is the excenter of triangle, of the triangle ABC here. So to find the excenter, what we did was we found these two angle bisectors, external angle bisectors, and intersected it with one of the angle bisectors, that's angle A, and then their intersection is what we call as the excenter. Now, if now we can also establish the relationship that LB is equals to LI. So if we were to draw a circle around this point, then L would be the center of the circle, because we can see that point A, I, L, and IA, they are collinear. And by this we mean that they lie on the same straight line. So we have found from this triangle, we have proved that LB is equals to LI, right? So what we can also prove is that LB is equals to Li is also equals to Lc, which is also equals to L to Ia. So we can see this chicken foot over here, like this. So point L is we can see the center, and these are the points to which it extends, and it has the equal distances to it. And this image right here looks like the chicken foot here. So you can see that this theorem is also known as the chicken foot lemma. So the theorem states that LB is equals to Li, and that AIL and IA, these points are collinear. And following this, from this simple proof, we can also like validate other theorems as well. So this is it for the chicken foot lemma. So thank you.